All right, guys, here is part 3 of the 10.3 notes. Like I said, it's a long section and kind of a tough one. So we're shifting gears now. We got done with squares there in the last two examples, and now we're going to move on to triangles right here. So remember, the whole purpose of this section is that we are dealing just with regular polygons. So we know for a fact then, because this problem is even in this section, that this is a regular triangle, otherwise known as an equilateral triangle. So it's going to be the same formula that we're going to be using here that we used in the last two, that the area of a regular polygon is going to be 1/2 times your perimeter times your apothem. Step 2, let's fill in what we know. So we've got a 1/2. Perimeter isn't going to be tough to figure out. This bottom side right here is going to be 8, and because it's regular, all three sides are the same length. So the 8 times 3 is going to give us a perimeter of 24 centimeters, but the apothem here is going to be the hard part. So, like I said earlier, we got to get used to drawing the apothem when it's not there. Now, for a reason I'm not going to try to get into over a video, if you were to think about where the apothem would be located, imagine dropping an altitude straight down here from the top vertex of a triangle all the way down to the midpoint of the opposite side, and the center of that triangle is located 2/3 of the way down that altitude right there. That's what we called a centroid back in chapter 5 when we did that. So this little piece right here in red, that's going to be your apothem. All right, and then again, we usually want to get used to drawing a radius right next to it if we haven't done that before. So we just formed a triangle with the apothem and the radius, and let's remember that we know this is a right angle right over here, but we've got a little work to try to do to figure out everything else that's going on in this figure. So, kind of like we did in the last problem, theta, the measure of our central angle, is going to be 360 divided by n, the number of sides in each figure, and in this case, n is just 3. That means that theta, the measure of our central angle, is 120 degrees, and this angle formed here between a radius and an apothem is always half of that central angle right there. So that's a 60-degree angle. So we have a 90 and a 60. That leaves a 30-degree angle for us right over here. And this was the reason why, back in the end of video number 1 on this section, we talked about the side length relationships in a 30, 60, 90 triangle. So what's going on in this one right over here? We know that the entire bottom side of the big triangle is 8. That means that this little piece right over here, which I usually call x, is going to have a length of 4. And that 4 there is the length of our long leg. What we need, though, is the apothem, the length of the short leg. So to figure that out, here we go. The apothem is going to be the long leg, which is 4, and then we're going to divide that by the square root of 3. All right, rationalizing that, and again, your calculator would do this work for you if you wanted, it's going to end up being 4 root 3 over 3, and unfortunately, guys, it doesn't get any simpler than that. So 4 root 3 over 3 is the length of our apothem. All right, so with all of that put in place here, we're ready to go ahead and multiply all this out, but again, this isn't going to be as nice as we would like it to be. Actually, it's not terrible. The 1/2 times the 24 right here is going to give us a 12. That 12 gets divided by that 3 to make a 4, and the 4 times the 4 root 3 is going to get us a 16 root 3 square centimeter area for that particular triangle there. All right, so what I'm hoping you guys are taking from that example and the next one is that every time we are dealing with a regular triangle or an equilateral triangle, this triangle that's formed by apothem, radius, and half of a side length is always going to be a 30, 60, 90. All right, let's take a look at another triangle example right here and see what we can do with this one. So again, we know that once more this is a regular polygon. So area of a regular poly is 1/2 times its perimeter times its apothem. And this one's different from the last one in that it was the apothem that was actually given to us. So we've got the 1/2. We don't know our perimeter just yet, but we do know that our apothem has a length of 5 millimeters, but we've got to try to figure out perimeter. So to do that, here we go. We're going to draw the radius now right next to that apothem. And just like in the last problem, this is still going to be a 60-degree angle. This is still going to be a 30-degree angle. And now in this case, the one side that we were given in this figure, this is actually easier than the last one, was the short leg. Okay, so let's remember what we know about 30, 60, 90 triangles. If your short leg is 5, the long leg, which you need right here, is always this short leg multiplied by the square root of 3. So this little piece down here, what I usually call x, is 5 root 3. So if x is 5 root 3, then s, which is the length of the entire bottom side down here, is always going to be 2 times x. So the 2 times the 5 root 3 is going to get us a 10 root 3 for the length of s. And now to find capital P, perimeter, we've got 1, 2, 3 of those sides in this figure. So we're going to multiply 3 times the 10 root 3 and come up with a 30 root 3 for the perimeter of this entire figure. Okay, and that is about all we can do with this one. The 30 times that 5 is going to give us 150, times 1/2 is going to be a 75 multiplied by the square root of 3. Everything was millimeters here, so our area is going to be in square millimeters. Okay, we're going to keep zipping right along and try to finish this one up in one more video. Hexagons are the third one that we're going to talk about and the last one that we're going to talk about within this section. So the story remains exactly the same. It's the same formula here, that area of a regular polygon is equal to 1/2 times perimeter times apothem. And in filling in what we know, we were given a side length down here of 10. So if we multiply that 10 by the 6 sides that we have, we're going to see that our perimeter here is going to be 60. But maybe not surprising, what we don't know in this figure is our apothem. So again, the apothem goes from the center of the figure straight down perpendicular to one of the sides. So that's our apothem. And I'm going to go ahead now and also draw a radius from the center to this bottom right corner over there. And that's going to be R, although we don't really need to know that too much in this case right here. Okay, since it's our first one with a hexagon, let's talk for a second about how to find theta. Now the formula we've been using is that theta, the measure of a central angle, is always 360 divided by n. Well, in a hexagon, n is always going to equal 6. So theta is 360 over 6, and that means that the measure of each central angle here is 60 degrees. Now, if you recall from earlier, that's the angle that we just found right here. That central angle is 60. What we're really interested in, though, is this angle right over here, which is always going to be half of what you came up with for theta. So that's a 30-degree angle. 30, here's a 90, and that means we've got a 60-degree angle right down here in that bottom right-hand corner. So actually, the interesting thing is, just like in the problems we were working earlier here with triangles, apothem, radius, and side length in a triangle gets you a 30, 60, 90, but it's one that I would describe as laying down. It's on its longer leg down here on the bottom. When you do the same thing within a hexagon, when you draw apothem and radius and use half a side length, you also get a 30, 60, 90, but this is what I would describe as a 30, 60, 90 standing up where it's resting on its shorter side. Okay, so what do we know then about the side lengths within this figure right here? Since the side length of the entire hexagon here is 10, we know that this piece right down here is half of that, which is going to be 5. And to get the apothem, you're going to take your short leg, which is 5, and multiply it by the square root of 3 to get 5 root 3 for the length of that apothem. And that should cover us, everybody. Half of 60 is 30. 30 times 5 is 150 times the square root of 3. And then we've got square inches for the area of that figure. And let's see if we can't finish up this last one here real quick. Okay, we've got a hexagon, and this time the apothem was given to us, but same formula. Area of a regular poly is 1/2 times perimeter times apothem. Okay, so area is going to be 1/2. We do not know our perimeter, but the apothem was given to us right here as 24. Okay, to find the perimeter, we got to focus on this little piece right down here that I like to call x. So I'm going to draw that radius in there, and just like in the last problem, we now just formed a 30, 60, 90 triangle. The 24 meter side right here that we were given was the long leg. So to find the short leg, which is going to be x, we are going to take our long leg, 24, and divide that by the square root of 3. When you put that in your calculator to rationalize that, you're going to end up with an 8 root 3 for the length of x. Now that's just part of it. S then which is the entire side length down here on the bottom, is going to be twice as big as that. So that's going to be 16 root 3. And to find the perimeter, we've got a total of 6 sides right there. So the 16 root 3 times 6 is going to get us 96 times the square root of 3 for your perimeter. Pretty big number right there. Okay, so let's put all this together right here. And I think for the first time I have to cheat and use my calculator here, everybody. So let's go ahead and type that in. The 0.5 for the 1/2 multiplied by 96 multiplied by 24 is going to get us an 1152. I didn't put the square root of 3 in my calculator. It just tags along for the ride, and we end up with 1,152 times the square root of 3 square meters.